Hi everyone, so today I have a short but interesting question for you, and today we're going to talk about binary integers and counting. So we're going to learn a little bit about this binary system, zeros and ones, basically binary representations, binary integers, and binary additions. How does binary addition work? We're going to talk a little bit about that, and after that we're also going to have a little bit of counting involved. So basic counting principles, the things that we study probably in your first lecture of permutations and combinations, really simple things. And this is one of those classic, number arithmetic puzzles. I'm sure you might have seen questions similar to this, although this might look a little bit more of a sophisticated version of that. But at the core of it is something that is fairly easy to do if you're able to understand what is going on in this situation, right? So let's just get right into it and you'll see for yourself what we're talking about. So this is the problem number 5 from the AIME in the year 2012. And in this video, we're going to talk about binary integers and binary addition, basic counting principles, book sessions of the AIME, and of course, a similar but challenging problem. So this is the problem number 5 from the AIME in the year 2012. And in this video, we're going to talk about binary integers and binary addition.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So it's telling us that let B be the set of all binary integers. So binary can only be 0 or 1. So binary integers means any number that consists of only 0 and 1, right? No other digits are permittable for us. You can only construct the numbers with 0 and 1, with the digits 0 and 1, okay? So let B be the set of binary integers, base 2 basically, that can be written using exactly 5 zeros and 8 ones. So basically we have, let's say, 13 places, right? So for the example, the number has, let's say, 13 digits, right? And those digits are obviously 0 and 1, and they're telling us that we have exactly 5 zeros and 8 ones. So let me maybe just write that. So 5 zeros plus 8 ones. So in total, we have like 13 places to fill in these digits, right? Where leading zeros are allowed. So you could have like 5 zeros, 8 ones, you could have 4 zeros and then 8 ones and then another 0 at the end. So leading zeros are basically allowed. You can start with 0. There's no restriction upon that. Then they are saying if all possible subtractions are performed in which one element of B is subtracted from another, find the number of times the answer 1 is obtained. So what they're essentially saying is take an element of B, let's say X, subtract that from Y, and you should get 1, right? And tell me the number of times this happens. So for how many elements does this happen, right? So essentially, for example, let's say, let me just make a very rough diagram. So let's say this represents the set B, and let's say these dots represent the numbers in this set B such that they satisfy this given condition, right? 5 zeros, 8, 1, binary integers, blah, blah, blah. And what I did is I took 2 elements from it. Let's say I took X and Y. Okay. Now this is asking when you subtracted X and Y, you got 1, right? So how many times is this happening? How many times does this happen that you take 2 elements from B, you subtract them and get 1? How many times does that happen, right? So instead of thinking that the subtraction is equal to 1, I can think it in an alternate way, because subtraction, subtracting these 2 digits, it's going to be very messy, right? Because subtraction of binary, secondly, it is 13 digits, and it can get really messy, really complicated. So what I can instead think of is, instead of thinking X minus Y is equal to 1, I can actually think of X as Y plus 1. Do you actually see what is happening over here? You took 1 element from B, which is Y, you added 1 to it, and then you got another element of B, right? So 1 element of B, you took 1 element of B, you added 1, and then you got another element of B. Isn't that fascinating? And this is actually a lot simpler to think about, because adding by 1 is very easy. If I tell you, let's say, what is 10 plus 1, it is 11. So adding is something that is more intuitive, that's easier to think about, right? And it's easier to work with. It's easier to count with addition in a way. It's easier to deal with number puzzles in this manner. So essentially what we're really trying to do is find out the number of times when you take any one element from B, add 1, and you get another element of B, right? And X comma Y obviously belong to this set B, right? So they're essentially asking how many times is this happening, right? Okay, so let's maybe discuss about this a little bit. So like we said, B, any element in B will have 13 places, right? We'll have 5 zeros and 8 ones. So in total, it will have, let's say, 13 places to fill up these digits. So let's say the number ends with 0. So we're considering y, right? So let y end with 0. And then we're going to add 1. So for example, y will have some 12 digits like this, and at the end it will have 0. So its last digit will be 0. Just considering this case. Now when you add 1, well, 0 plus 1 becomes 1. And this is as it is. Now, do you see the problem over here? Here we had how many ones? We had 8 ones, because y is an element of B. So we'll have 8 ones in this. So effectively here also we'll have 8 ones. But then we got another one. So in total it will have x, which is y plus 1 is equal to x. X will have 9 ones. But if it has 9 ones, it cannot be an element of B, because if it's an element of B, it strictly needs to have only 5 zeros and 8 ones. Exactly 5 zeros and 8 ones, right? So if X is having 9 ones, that means it cannot be an element of B. Therefore, Y cannot end with 1, right? So this case, sorry, Y cannot end with 0, right? We're considering 0, right? Sorry about that. So the case where y ends with 0 does not work. But now since we're really dealing with binary, therefore y has to end with 1, isn't it? Right? So y has to end with 1. So basically the number y, the binary integer y, will look something like this. We have some 12 digits. I don't know what they are. I don't even care what they are. At the end we have 1. Now again, in this scenario, we're going to add 1 to it, and then we're going to see what is going to happen. Now, if this was normal addition, we would have 1 plus 1 is equal to 2. But this is binary. 2 is not permissible. We can only deal with zeros and ones. So what really happens is that you get a 0 over here, and then you carry over this 1. Right? So you'll not write 2. You'll get a 0, and then you'll carry over the 1. Now, here really we can split it up into 2 cases. Let's consider the second last digit. Now, if the second last digit over here is 0, well, 1 plus 0 is simply equal to 1. Now, do you notice what is happening over here? You had this 1 over here which gets converted into a 0. So you lose a 1. But over here you had 0, and then that gets converted to 1. So you gain a 1, and the rest all is obviously the same. So you lose a 1, you gain a 1. Therefore, you still at the end of the day have 5 zeros and 8 ones. So that means this X is indeed an element of B. Therefore, if Y ends with 0, 1 as the last 2 digit, it works. Right? It works amazingly well. So for example, Y will look something like you have 11 digits. I don't know what they are. I neither care what they are. The 12th one will be 0 and the 13th one will be 1. So it will look something like this. So now, yeah, we just consider the case where this is second last digit is 0. Let's just consider when the second last digit is equal to 1. Let's see what happens. So we had some representation like this. We had second last and last is equal to 1. And then as before, we are adding 1. 1 plus 1, well, you get a 0 and you get 1 carried over. Again, 1 plus 1, you get a 0 and then you get carried over 1. Now, do you actually realize what's happening? This 1 becomes 0. So you're losing a 1. Now again, this 1 becomes 0. So you're again losing a 1. So therefore, we lose 2 ones. We lose 2 ones. And no matter what the third digit is, no matter what the third last digit is, whether it be 0, whether it be 1, whether it be anything, 0, 1 doesn't matter. You're never going to recover these 2 ones. At the best, you're only going to be able to recover 1 1. Right? You're never going to be able to recover 2 ones or more ones. For example, if we have a 1 over here, well, the process continues, right? You get 0 and then you get carried over. In this case, you lose 3 ones. Because this one again gets converted into 0. And even if you have, let's say, a 0 over here, you get, let's say, 1 over here. But then still, this 0 gets converted into 1. But then you lose 2 ones and then you recover 1. So still 1 is still lost. But we need exactly 8 ones. And over here, X will at the very maximum have 7 ones. Are you understanding what is happening? So basically, if I have the second last digit as 1 and the last digit as 1, I will lose 2 zeros. I will lose 2 ones, and I'll never be able to recover those 2 ones. So this case also fails. So the only way where I'm taking an element from B, adding 1 and getting another element from B is when that element of B looks something like 11 digits, 12th will be 0, 13th will be 1. Like I said over here, this case that works. And this is in fact the only case that works. So therefore Y has in a way 13 places, and it needs to be filled with 5 zeros and 8 ones. Now let's just do some basic PNC over here. Well, 2 are fixed, right? So 2 are fixed. Out of them, 11 places are permutable, or let's say it is variable. And these 11 places will have 5, because we have 1 0 over here. So 5 minus 1, 4 zeros. And similarly 8 ones, but we have 1 already fixed and 7 ones. Well, 11 places, 4 zeros. How many ways are there to do that? It's obviously 11C4, which so happens to be 330, and that is our answer. Well, why does this work, if you might say? Well, just think of it like this. You have 11 places, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? Let's say we have 11 places. And once you fix these 4 zeros, for example, 1, 2, 3, and 4, once you fix these 4 zeros, the other places automatically have to be 1. So you really don't have a choice. They have to be 1. Everything else has to be 1. That's it. 1, 2, 3, 4, 5, 6, everything else has to be 1. So really, you're only permuting the zeros. 11C4, which is 330. Or alternatively, you could permute the ones. You could say that, okay, I have 11 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I could place the ones. 1, 2, 3, 4, 5, 6, and 7. So you have 11C7 ways to do that. And then automatically, everything else becomes 0. And 11C7 is actually also 330 because of the simple fact that 11 choose 4 is actually equal to 11 choose 7. So no matter how you do it, the answer really is 330. So that was a very interesting question. It's one of those classic number arithmetic puzzles where you have to deal with subtraction or addition, and this is maybe a little bit of a trickier version of that because it dealt with binary counting and binary addition and those sort of things. But I hope you learned a little bit from that, and now you can deal with binary additions as well. Okay, so we have some book sessions for USAMO, JMO, and AIME. Elementary number 3 by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Props in Plane Geometry by Sharikin, Elementary number 3 by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. Okay, so you have a similar but challenging problem, and I want you to find all positive integers n so that both n and n square are palindromes when written in binary, that is base 2 without leading zeros. Palindrome is any number that is read the same forward and backwards. For example, 101 is a palindrome because you read it from this way, you get 101, you read it from this way, again you get 101. Right? So no matter how, in what way you read it, right to left or left to right, you'll still get the same number, you'll still get the same combination of digits, right? So the question asks you to find all positive integers n so that both n and n square are palindromes when written in binary, base 2, without leading zeros. For example, you cannot start with 0 and you cannot follow up with certain zeros. It has to start with 1 basically. So maybe try this out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.